This is Dr. Shankaraiah from Department of Physics. In this presentation, I am going to discuss question bank on Module 4, Part B, long answer questions. We have discussed the earlier 10 questions in last presentation. So today I'll start with 11th. So explain Meissner effect and explain in detail. Okay. So we need to explain what is Meissner effect in detail. So in 1933, Meissner and Ostenfeld found that when superconductors are cooled below the critical temperature, in the presence of a magnetic field, magnetic flux is expelled from the interior of the specimen and the superconductor becomes a perfect diamagnetic, and this effect is known as Meissner effect. You can see that clearly from this picture. So when T greater than Tc or H greater than Hc, the material is in normal state and all the whatever magnetic field you apply, the magnetic flux lines can penetrate through the material. But when T is less than Tc or Hc is less than Hc, the material goes from this normal state to superconducting state. When the material goes to superconducting state, if you apply magnetic field, all the flux lines are expelled by this material. Okay, so this effect or expulsion of applied magnetic field is called as Meissner effect because the scientist Meissner observed this in superconductors. So the magnetic induction or the magnetic flux lines per unit area inside the specimen when T is less than Tc is this: B is equal to mu naught into H plus M. We know that M is equal to chi into H. So when you substitute this here, you will get mu naught into H into 1 plus chi. Okay. So where M is the magnetization inside the material and H is the applied magnetic field. Okay. So when T less than Tc, we know that magnetic induction is 0 because the material expels the applied magnetic field. Okay. So that means B is equal 0. When T less than Tc, B is equal 0, that means the equation for B, which is mu naught into 1 plus chi into H is equal to 0. That means mu naught into 1 plus chi into H is equal to 0, or so from this equation H plus M, right? So we can take the first equation. B is equal to mu naught into H plus M is equal to 0. So that means mu naught into H plus M is equal to 0. That means H plus M is equal to 0, or H is equal to minus M, or M by H is equal to minus 1. But M by H is the susceptibility chi. Okay, so whenever the material exhibit this Meissner effect, you can find out the susceptibility is negative, and susceptibility is negative for a diamagnetic material. Okay, so Meissner effect is also called as perfect diamagnetism. Superconductor exhibit this perfect diamagnetism when T less than Tc. Okay, so these two independent properties, namely zero resistivity and perfect diamagnetism, are the two properties by which you can identify whether the material is a superconductor or normal conductor. So the second question, what do you mean by perfect diamagnetism of a superconductor? So just now we have discussed what is perfect diamagnetism. So Meissner effect, we know what is Meissner effect. When we cool the material below Tc, we will find that the material will go from normal state to superconducting state. In the normal state, whatever magnetic field you apply, the magnetic flux lines pass through the material. Okay, but with T less than Tc, when the material goes into superconducting state, whatever magnetic field you apply, the magnetic flux lines are expelled by the material, and this is called this is called Meissner effect. And yeah, so in the Meissner effect, the magnetic induction B is equal to mu naught into H plus M. B is equal 0 when T less than Tc are in the superconducting state. Okay, so B is equal 0 gives mu naught into H plus M is equal 0, or chi is equal to minus 1, which is M by H. Okay, so chi is minus 1 is only for diamagnetic material. So superconductor exhibit this perfect diamagnetism when T less than Tc. Distinguish between superconductor and normal metal. We know that metals are good conductors of electricity because they contain tremendous number of free electrons, and the low resistance offered by these free electrons is attributed to the scattering of free electrons by the vibrating ions of the lattice. So if you think of metal as a lattice, each lattice site is occupied by a positive ion and all the free electrons are roaming around in this lattice. Okay, if there are no defects, or impurities present in this metal, the resistance offered is very low, and even when you cool the metals, even when temperature increases, the amplitude of the lattice vibrations increases and scattering of the electrons increases and leading to no resistance. Okay. When you cool the metal to 0 Kelvin, even then you will find there is some resistance, finite resistance, which is called residual resistance, and this residual resistance is coming from the scattering of the electrons by the impurities and the crystal defects present in the material. So that can be understood by using this graph very clearly. Okay, if you have a normal metal, so this is the behavior of normal metal. So y-axis is resistivity. I am plotting resistivity versus temperature. Okay, so resistivity versus temperature graphs clearly showing that as I decrease the temperature, the resistivity of this metal decreases, but even if I decrease the temperature to 0, even then there is some finite resistance. This is called a residual resistance in metals. Okay, but this is about a metal. Okay, metal has tremendous number of free electrons, but that is the reason why you have metals are good conductors of current, but temperature dependence of resistivity in metals is seen here clearly, that as you cool the metal to 0, absolute 0 Kelvin, also you find that there is some residual resistance. The residual resistance is coming because of the impurities or defects present in the material. Okay, so that is about metal. Superconductor, on the other hand, as you cool the superconductor below a certain temperature called Tc, you will find the resistance drops suddenly to 0. Okay, so this is observed in mercury first by Kamerlingh-Onnes in 1911, and the critical temperature Tc is around 4.15 Kelvin. Okay, so superconductors have no resistance. The resistance is 0. That is why these materials are called as superconductors. Okay, so that can be understood clearly by using this graph. Okay, so superconductivity is a phenomenon in which electrical resistance of the material suddenly disappears below a certain temperature, and the materials that exhibit this superconductivity are called as superconductors. Give an account of the phenomenon of superconductivity. So just now we have discussed what is superconductivity. So superconductivity is a phenomenon in which the electrical resistivity of material suddenly disappears below a certain temperature. This is called superconductivity, and the materials that exhibit this superconductivity are called superconductors. And superconductivity is initially discovered by Kamerlingh-Onnes in highly purified mercury in 1911, and the critical temperature was around 4.15 Kelvin. But later on, this superconductivity is also observed in different materials, for example, lead, zinc, aluminum, and other metals and alloys. Okay, so this is about superconductivity. What is the significance of critical temperature, critical magnetic field, and critical current density for superconductors? So we need to discuss about critical temperature, critical magnetic field, and critical current density. Okay, so critical temperature. When a superconducting material is cooled below a certain temperature, it goes into a superconducting state from the normal state. Okay, so the temperature at which a material in normal state goes into superconducting state is called as critical temperature, and different materials have different superconducting materials have different critical temperatures, and this transition is also reversible. I mean, as we increase the temperature above Tc, the material will go from superconducting state to normal state, right? So this transition is reversible, and this is a thermodynamic transition. Okay, so this is critical temperature. Critical magnetic field. Superconducting state depends on the strength of the magnetic field in which the material is placed. Superconductivity vanishes if a sufficiently strong magnetic field is applied. Okay, if a field H greater than Hc applied to a material, then the superconducting state is destroyed and the material will go into normal state. Okay, so the minimum magnetic field which is necessary to regain the normal resistivity is called critical magnetic field Hc. Okay, and the magnetic field exceeds this critical magnetic field, then the material will go from superconducting state to normal state. So this is the variation of critical magnetic field with temperature. Below Tc, the material is in superconducting state, and also below Hc, the material is in superconducting state. If you increase the temperature above Tc, the material will go into normal state. Also, if you increase the field greater than Hc, again the material will also go from superconducting state to normal state. So the variation of the critical field, so this is very important. The variation of critical field with temperature is Hc of T is equal to Hc of 0 into 1 minus T square by Tc square. Okay, so this is very important equation which is used to calculate different parameters. For example, critical field at finite temperature, or critical field at absolute 0 Kelvin, or you can also calculate critical temperature for different materials given critical field at finite and 0 Kelvins. Okay. Critical current density. So to destroy the superconducting state, you don't need to apply external magnetic field, but you can destroy the superconducting state by increasing the current flowing in the superconducting ring. Okay. So the superconducting ring carries a current I, gives rise to its own magnetic field. If as the current flowing in the superconducting ring, it generates magnetic field. As the current increases to a critical value IC, if you increase the current that is flowing in the superconducting ring, the current that is flowing in the superconducting ring will also generate or produce magnetic field. So if you increase the current to a critical field value IC, then the magnetic field that is produced by this critical current will also increases to HC. Okay, when the field, when the current increases I greater than IC, then the field also increases, goes beyond this HC, and the superconducting state will be destroyed and the material will go into normal state. So the maximum current density at which the superconductivity disappears is called as critical current density. So the critical current density is given by this formula. IC is equal to 2 pi R HC, and this condition that when the critical current density is less than, when the current density is less than the critical current density, the material will be in superconducting state, and when the current density is greater than the critical current density, the material will go from superconducting state to normal state, and this is observed by scientists named Silsby, and this and hence it is called as Silsby effect. Okay, so in this formula of critical current IC is equal to pi R HC, R is the radius of the coil and HC is the critical magnetic field. So this is the variation of all these three parameters: critical current density and critical magnetic field and critical temperature. So below critical current density, the material will be in superconducting state. Below critical transition, the transition temperature, material is in superconducting state, and also below critical magnetic field, the material is in superconducting. So this is all in superconducting state. Above this, you will get the material will go from superconducting state to normal state. What is superconductivity, and describe type 1 and type 2 superconductors. So we have discussed what is superconductivity. Superconductivity is a phenomenon in which the resistance, the electrical resistance of material suddenly disappears below a transition temperature, and the materials that exhibit superconductivity are called superconductors. The first superconductivity is observed by in pure mercury by cooling down to zero by cooling, and the critical transition temperature is observed by Kamerlin Arnes as 4.15 in mercury. Okay, so that is about superconductivity, and superconductors are divided into two categories depending on the way in which transition from superconducting state to normal state proceeds when the externally applied magnetic field exceeds Hc. Okay, so how do we classify superconductors into two categories? Based on the transition, how the material will go from superconducting state to normal state, whether the material is going from superconducting state to normal state in a sharp way or is it going in a gradual way. Based on that, we do classify superconductors into two categories. So type 1 superconductors, the transition from superconducting state to normal state in the presence of magnetic field occurs sharply at the critical value of Hc. Okay, so we can see clearly here. So the resistivity versus critical field, as the field increases at Hc, the material has gone from superconducting state to normal state. So the sharp transition, superconducting state to normal state as a sharp transition in type 1 superconductors, and this is the magnetization versus external magnetic field. When the material is in superconducting state, the magnetization increases and it goes to zero above this critical field, then the material goes into normal state. So type 1 superconductors are also called as soft superconductors, and the magnetic field that is produced by type 1 superconductors is very less, around 100 to 2000 Gauss, and hence they are not much of use in production of high magnetic fields. Okay, so these are some characteristics of type 1 superconductors as we discussed just now. And type 2 superconductors in type 2 superconductors, the transition from superconducting, so this is superconducting state, so the transition from superconducting state to normal state is it is in gradual manner. That means as you increase the field above HC1, the resistance slowly starts increasing, and it reaches to a saturation at HC2, and then the material will go from superconducting state to normal state. In between HC1 and HC2, you have a mixed state. Okay, so in type 2 superconductors, you don't have simply superconducting state and normal state. In between, you also have a mixed state. Basically, you have three different states in type 2 superconductors as you increase the field from at 0 to a critical values. Okay, so these type 2 superconductors are discovered by Chudnikov in 1930s and explained by Abrikosov in 1957. These type 2 superconductors have two critical fields, Hc1 and Hc2. Between Hc1 and Hc2, you have mixed state, whereas below Hc1 you have superconducting state, and above Hc2 you have normal state. So this is the variation of magnetization versus critical field. So you can see this is a superconducting state where you have perfect diamagnetism, and you have a mixed state between Hc1 and Hc2, and above Hc2 you have normal state. So type 2 superconductors produce high magnetic fields, and they are used in production wherever you need to produce maximum magnetic fields. Okay, so these can produce around 20 to 50 Webers per meter square, and yeah, so these are some characteristics of type 2 superconductors. Explain the BCS theory with keynote of Cooper pairs. Okay, so the BCS theory is first explained by three scientists, Bardeen, Cooper and Striefers, and this theory is a quantum mechanical theory of superconductivity, which is known as BCS theory, for which they have awarded Nobel Prize in 1972. So BCS theory is assumed the interaction of two electrons through quanta of lattice vibrations. Okay, so the zero electrical resistance in superconductivity is explained by this BCS theory using the main important point in BCS theory that explains zero electrical resistance is that two electrons interact through a quantum vibration or lattice vibration, which is called as phonon. Okay. So the two principal features of BCS theory is that electrons form pairs called Cooper pairs, which propagate through the lattice, and such propagation is without resistance because electrons move in resonance with the phonons. Because of this electron movement without resistance, we get zero electrical resistance in superconducting state, and through this is through phonon. So a phonon is a quantum mechanical description of an elementary vibrational motion in which a lattice of atoms or molecules uniformly oscillate at a single frequency. Okay, so that is why we are saying that electrons move in resonance with phonons. Okay, so phonon is nothing but lattice vibration. Okay. So this is to explain the BCS theory, how these Cooper pairs move. So this is electron 1 and electron 2, and this is the ion. So if you think of this as a lattice or superconductor, so you have lattice site, each lattice site. So all these atoms have lost their electrons. So that is why they have become positively charged ions, and all the free electrons. So these lattice sites are occupied by positively charged ions, and the electrons are moving in this lattice. Okay, so the pair of electrons, when they come closer, because of their same electric charge, they will repel, and they will come closer because they are attracted by this positive nucleus. Okay, because of this movement of electron pair, we get this kind of vibration of the lattice, and hence it is called as phonon. Okay, so in equilibrium condition, a balance between attraction and repulsion is established. Attraction between the positive nucleus and negatively charged electron, and repulsion between the two electrons. Okay, so in equilibrium condition there will be a balance, and 2 electrons combine to form a Cooper pair. In normal temperature, attractive force is too small and pairing of electrons does not take place. However, at lower temperature, the pairing is energetically advantageous. In typical superconductor, the dense cloud of Cooper pairs form a collective state and the motion of the all Cooper pairs is correlated. Such pairs drift cooperatively through the materials. Thus, superconducting state is an ordered state of these conduction electrons. Since the density of Cooper pairs is very high, even large current require only a very small velocity. Because of there are so many tremendous number of electrons present in the superconducting state, even small velocity is enough to produce large currents. Okay, so that is the reason why the small velocity of ordered Cooper pairs minimize collision processes and ends to zero resistivity that is observed in superconductors. So yeah, so you can look at the energy gap between in the superconducting state and in normal state. So BCS theory predicted the existence of energy gap between the ground state, which is superconducting state, and excited state is the normal state. Okay, the energy gap represents the energy required to break up a Cooper pair, because there are Cooper pairs present in the superconducting state. If you want to convert the superconducting state to normal state, you need to supply energy which is required to break this Cooper pair. Okay, so according to this BCS theory, the energy gap at 0 Kelvin is around 10 power minus 3 electron volts. Describe Meissner effect and soft and hard superconductors. So we have discussed what is Meissner effect. So expulsion of external field when temperature is reduced below Tc. So this we have discussed, and when below Tc, we know that the magnetic induction is 0, and hence we can find out that chi, which is m by h, is -1. So that means susceptibility is negative only for diamagnetic material. So when the material is in superconducting state, it acts as perfect diamagnetic material. Okay, so yeah, that is. And type 1, type 2 superconductors we have just discussed just now. So these are classified based on the transition from superconducting state to normal state. In type 1 superconductors, the transition is very sharp from superconducting state to normal state as the field is increased, whereas in type 2 superconductor, the transition is gradual from superconducting state to normal state. In between, you have a mixed state between the two critical fields, Hc1 and Hc2. Okay. So, 19th question, explain the various properties and important applications of superconductors. Superconductors exhibit many unusual and interesting properties. The first one is zero electrical resistance. We have discussed just now. A superconducting ring is taken in the normal state and kept in a magnetic field. And if we cool this superconducting ring below the critical temperature, we will find that the material will go from normal state to superconducting state. And when the external magnetic field is switched off, we will find there is current induced in the ring. So because there is no resistance in the superconducting state, this current that is induced in the ring will flow forever. And we can find out whether there is resistance or not in the superconducting state. We can take a test coil close to the superconducting ring, and if there is any change in the current, there will be a change in the magnetic field that is induced by the current. And if there is any change in the magnetic field, we will find the current in the test coil that which we have used. So since careful experiments found out that there is no change in the resistance is zero in the superconducting state. So when the material is in the superconducting state, the current that is induced in the superconducting ring by changing the magnetic field, once the current is started in a closed loop of superconducting material, it will continue to keep flowing without diminishing in strength. Okay, such a current is called persistent current, because there are no power losses in superconducting state. Because resistance is zero, the current that is induced in a superconducting ring can flow up to 1 lakh years once it is induced in a superconducting ring. Okay, so the important property of superconductor is this persistent current, because that will flow forever. Critical temperature, we have just now discussed. The material which is in normal state, if we cool the material below the critical temperature, the material will go from normal state to superconducting state. So we are defining temperature at which the material will go from normal state to superconducting state as the critical temperature. So critical magnetic field. So when we apply the magnetic field above a certain critical field, we will find the material will go from superconducting state to normal state. So the minimum magnetic field which is necessary to regain the normal resistivity is called critical field. Okay. So this is the variation of critical field with temperature, and this is the critical field with temperature, and Hc of T is the critical field at finite temperature. Hc of 0 is the critical field at absolute 0 Kelvin. We can destroy the superconducting state not only by applying the magnetic field, but by internal current that is flowing in the superconducting ring can it also destroy the superconducting state. If we increase the current to a critical above a critical value IC, then the magnetic field that is produced by this current also increases beyond this Hc, and then the superconducting state is will be destroyed to a normal state. So that current above which the material will go from superconducting state to normal state is called as critical current density, and this is the variation of critical current with critical field and radius, and this effect is called as Silsby effect. When the density current density is less than the critical density, the material will be in superconducting state, and the density is greater than the critical density, the material will go from superconducting state to normal state. And the last property of superconducting material is Meissner effect, and we have discussed it many times now. Okay, so the applications. So superconductors are used in many applications in medicine and as well as in transformers and electrical machines, research and diagnostic equipment in medicines, very fast electronic switches. We can use superconductors. We can also use them as cryotrons. We can also, the very important application of superconductors is magnetic levitation trains, because of this Meissner effect. Because of the Meissner effect, whatever field you apply, the superconductor will repel. So hence, if you have a superconducting trail and magnetic trains, the magnetic train will float in the air, and they are called as magnetic or maglev trains. And the last one is SQUID, superconducting quantum interference device, which can be used to measure even very extremely magnetic flux, which is we act as sensitive magnetometer. So the last question is that explain Meissner effect and magnetic levitation. So we have discussed the magnetic Meissner effect or perfect diamagnetism now so many times, and the application or magnetic levitation. The one of the important application of this Meissner effect or superconductor is maglev trains. Okay, so Meissner effect is the standard test used to conclusively prove whether the material is in superconducting state or normal state. A material in superconducting state acts as a perfect diamagnet and hence strongly repels the external magnets. Okay, so this is called as levitation effect, and this levitation effect is used in the operation of maglev trains. So these are some of the textbooks used and reference books to look at, and to summarize, I have discussed the long answer questions on module 4, which is magnetics in superconducting materials. So in this presentation, I have discussed the long answer questions on superconducting materials. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.